Usually when we talk about software, there's this underlying expectation of total subservience. Like, think about a physical map, right?
Right.
Unfold it on your dashboard, you trace your finger along the route, and the map just sits there. I mean, it gives you data, sure, but you have to do all the actual driving. You are the engine. You're the navigator.
Yeah, because for decades, software has essentially been a static reference tool.
Yeah.
I mean, it responds to a specific query, but the cognitive load, the planning and execution that rests entirely on the human.
Right. But then you step into the world of artificial intelligence as it stands right this very minute, and suddenly that map isn't just sitting there. It's ripping itself out of your hands, climbing behind the steering wheel, driving you to your destination, rerouting around a closed bridge, and like casually picking up your dry cleaning on the way.
Exactly.
We are looking at a technological landscape that is aggressively transitioning from reactive tools to proactive engines.
It is the absolute definition of a paradigm shift. I mean, we are moving from the era of the oracle, where you ask a question and get an answer, to the era of the agent.
And if you are an undergrad right now, studying computer science, engineering, or honestly just trying to figure out what the tech industry is going to look like when you graduate, this deep dive is built specifically for you.
Yeah, it really is.
We've taken a towering stack of research papers, GitHub repository updates, and press releases from just the past 7 days, specifically the week leading up to Sunday, May 24, 2026.
Which has been an incredible week.
Oh, absolutely wild. Our goal here is to filter out the marketing noise and look at the actual computer science. We're going to explore this shift to agentic systems, then look at the massive leaps in hardware efficiency making it possible, the very real geopolitical and physical friction this tech is hitting, and finally, the incredible ways applied machine learning is solving hard scientific problems today.
And looking at our sources from just the last 7 days, the velocity of deployment is staggering. I mean, a single week right now is enough to render an entire semester's curriculum obsolete.
Okay, let's unpack this. We have to start with the concept of the agent. Because this week, the industry didn't just hint at a shift, right? They planted a massive flag in the ground.
They absolutely did.
Google I/O 2026 just wrapped up, and they explicitly declared the, quote, agentic Gemini era. The Gemini app is transitioning into a proactive 24/7 helper. Alongside that, they launched managed agents in their API and a platform called Google Anti-Gravity 2.0.
Right, which is huge.
Yeah, it's designed entirely as an agentic development environment. So mathematically speaking, is an agent just like a standard large language model wrapped in a recursive Python loop?
Well, that's a great way to visualize it conceptually, but architecturally, it's much more profound. What's fascinating here is the pivot from stateless to stateful interactions. Because for the past 3 years, the dominant paradigm for interacting with an LLM has been stateless. You send a prompt via an API, the model computes the probabilities, sends back a string of text, and then immediately forgets you exist.
Just a clean slate every time.
Exactly. What Google is doing with Anti-Gravity 2.0 and managed agents is providing native infrastructure for goal-oriented stateful loops.
Meaning the system actually has a persistent memory of its own actions.
Yeah, precisely. Instead of treating the AI as a function called, input, output, terminate, you treat it as a daemon process running in the background of an operating system. You don't give an agent a prompt, you give it a goal.
And that just runs with it.
Right. The orchestration layer takes that goal, breaks it down into subtasks, plans a sequence, writes the code, executes it, evaluates the output, recognizes its own errors, and the course corrects. It requires access to tools, like a browser or a terminal, and a really sophisticated memory management system to maintain context.
I like to think of the difference like this. A chatbot is an encyclopedia, but an agent is an intern.
I like that analogy.
Right. You ask an encyclopedia a question, it gives you a fact. But you give an intern a goal, and they figure out the steps, use whatever tools they need, get confused, figure it out, and come back with a finished product.
That is precisely the dynamic.
Yeah.
And the arms race to build the best intern is accelerating rapidly. Just this week, we saw reports that DeepSeek, the Beijing-based lab that completely disrupted the market with their V3 and R1 reasoning models, they're forming a dedicated harness team.
Oh, wow. Harness team.
Yeah, their sole mandate is to build a coding agent product to rival Anthropic's Claude Code.
Yeah.
So they are shifting their engineering focus from foundational model training to autonomous digital worker deployment.
And it isn't just corporate giants doing this, right? The open source research community is flooding the zone with multi-agent frameworks. Like Looking at the trending papers on Archive this week, there was one called MOSS, and this honestly blew my mind.
Oh, the MOSS paper, yeah.
It's an autonomous agent system focused on, quote, self-evolution through source-level rewriting.
Yes, the MOSS paper is a really significant technical milestone. When we say source-level rewriting, we don't mean the agent is just, generating boilerplate code for a user's web app.
Right. It's not just writing HTML.
Exactly. The agent is analyzing its own underlying architecture. It's scanning its own abstract syntax tree, the structural representation of its code, finding algorithmic inefficiencies, rewriting that code, and deploying the optimized version of itself.
Wait. But if an AI is actively rewriting its own foundational source code, how does it not just instantly break production? I mean, if I change one wrong variable in a script, the whole thing crashes. How does an agent survive its own edits?
Through rigorous sandbox validation loops. The agent doesn't just rewrite the code and hit save on the live server. That would be catastrophic.
Yeah, obviously.
He writes the new module, compiles it in an isolated container, and runs a battery of automated unit tests. It essentially benchmarks its new self against its old self.
Oh, that's wild. So it's competing with itself.
Yeah. And if the new code fails or runs slower, the agent discards it and tries a different approach. It's essentially evolutionary biology applied to software architecture. For a computer science student, this challenges the entire premise of static software deployment. The software you push to production on Friday might have entirely reorganized its own dependency graph by Monday to run 20% faster.
That is just wild to think about. And we saw another paper called Terminal World that pushes this autonomy even further.
Right, I saw that one too.
Instead of testing agents on how well they can pass a standardized test or chat with a human, they are benchmarking agents entirely on real-world command line terminal tasks.
Yeah, the Bash terminal is the ultimate unforgiving proving ground. A graphical user interface, GUI, is designed with affordances for human intuition. Buttons, visual hierarchy, error pop-up.
It'll hold your hand.
Exactly. A terminal is raw text. It expects precise syntax.
Yeah.
If an agent can navigate a Linux file system, resolve a broken package dependency, configure a firewall, and spit up a web server purely through the command line, it has achieved a level of operational autonomy that is immediately commercially viable.
And Terminal World is scoring that.
Right. Terminal World provides a rigorous, standardized benchmark to score that exact capability.
And taking that concept of autonomy and multiplying it, another paper introduced Claude AI Lab. This isn't just a single agent running terminal commands, it's an autonomous multi-agent research team.
Yes, a full team.
You have one agent initialized as the principal investigator, one as the literature reviewer, and another as the data scientist.
It's a great instantiation of cooperative multi-agent dynamics. The literature reviewer agent might scrape archive for the latest papers on a specific molecular structure, right? It synthesizes that data and passes it to the data scientist agent, which writes a Python script to model the molecule. The principal investigator agent reviews the model, finds a flaw in the methodology, and kicks it back to the data scientist for revision.
Which sounds incredibly powerful, but it brings up a huge technical hurdle that Hugging Face addressed this week in a brilliant technical blog post. It was titled, "Software Forgets. Agent traces are the memory."
That was a crucial read.
Right, because if you have these multi-agent teams running loops for days, eventually they hit the limit of their context window. How do they not just completely forget what the original goal was?
Memory management is arguably the biggest bottleneck in agentic systems right now. Standard models process text through a fixed context window. If the context window is 1,000,000 tokens, and the agent generates 1,000,001 tokens of internal dialogue and code, it literally pushes its original instructions out of its memory buffer.
It just overwrites its own purpose.
Exactly. So Hugging Face highlighted a shift towards structured episodic memory.
Okay, but how does that differ from just dumping everything into a standard vector database, like what we've been doing with RAG retrieval augmented generation for the last 2 years?
Well, RAG is great for semantic retrieval, finding a document that conceptually matches a query.
Yeah.
But it lacks sequential awareness. The agentic trace paradigm structures memory as a chronological ledger of actions and state changes.
So it's more like a timeline.
Yes, exactly.
Yeah.
The agent doesn't just remember what it read, it remembers why it ran a specific Python script 3 hours ago, what the error output was, and how that changed the file system. It stores the state deltas, not just the raw text.
Oh, wow.
Yeah, so it allows the agent to maintain a coherent narrative of its own workflow over long time horizons.
But let me push back on this whole multi-agent concept for a second. Let's say we have frameworks running massive multi-agent simulations, like the newly updated AgentScope 1.0 mentioned in our stats. If I have a firm with 5 AI agents working together, aren't we just compounding the hallucination problem exponentially? Like, if the data scientist agent hallucinates a fake statistical variance and passes it to the principal investigator, who then builds an entire thesis around it, doesn't the whole multi-agent firm just collapse into a spiral of confident nonsense?
It's a very real risk. It's a critical vulnerability known in systems engineering as a cascading failure. When agents consume each other's outputs without independent, skeptical verification, a single hallucination acts like a virus infecting the entire data pipeline.
So how do you stop it?
The mitigation strategies we are seeing deployed this week rely heavily on adversarial validation. You don't build a multi-agent system where everyone just agrees with each other. You explicitly build in red team agents.
Like an AI skeptic.
Exactly. You instantiate an agent whose system prompt strictly mandates that its only objective is to find mathematical or logical flaws in the other agent's work.
Oh, I love that. Just a built-in hater.
Basically, yeah. It aggressively audits, doubts, and tries to break the reasoning before the final output is allowed to proceed to the next step. It is essentially forcing the scientific method, rigorous peer review and falsification natively into the execution loop.
Okay, that makes sense. But practically speaking, having 5 different AI models rigorously debating every single step of a complex problem, running red team audits for hours, I mean, the compute cost would be astronomical. The API bills would bankrupt a startup in a week.
Without a doubt.
Which means this entire agentic era is just a theoretical playground for massive tech monopolies unless the underlying intelligence gets exponentially cheaper and faster.
Which brings us perfectly to the underlying physics and economics of the space, because the agentic era is entirely gated by the cost of inference.
And this week, the cost of inference entered a freefall while the speeds just broke the sound barrier. Let's talk about the efficiency wars.
Let's do it.
First, pricing. DeepSeek just dropped a massive 75% price cut on their V4 Pro model. According to the tracking site Artificial Analysis, it immediately topped the global bang for buck ranking.
Yeah, 75% price cut on a frontier-level reasoning model fundamentally alters the unit economics of computer science. Think about a task like having an AI read, categorize, and summarize 10,000 internal enterprise emails every night to flag compliance risks.
Right, massive data processing.
At last year's API prices, that might have cost a company thousands of dollars a month. Financially unviable, but with the 75% price collapse, that same task becomes a trivial line item. It transitions complex reasoning from a luxury resource to a ubiquitous commodity.
And then there is the raw speed. Over in China, Zhipu AI launched the GLM-5.1 high-speed API, and they hit an astonishing 400 tokens per second. They're calling it a new global benchmark.
It's an incredible technical achievement.
But let's contextualize this for the listener, because human reading speed tops out at maybe 10 or 15 tokens a second. If a model is spitting out text at 400 tokens a second, it obviously isn't meant for human eyes to read along. So why does that speed actually matter?
Well, high-speed inference serves 2 completely different masters. The first is time to first token, or TTFT, in the context of voice. If you want a seamless, interruptible voice conversation with an AI where it actually feels like you are talking to a human, the latency has to be under 300 milliseconds.
Right. Otherwise, it feels like a bad satellite connection.
Exactly. If the model can generate text at 400 tokens per second, it means it can synthesize the first few words of its response almost instantly, allowing the text-to-speech engine to start talking while the rest of the sentence is still being calculated. It eliminates the awkward walkie-talkie pause.
And the second master?
Internal agentic monologues. Going back to our multi-agent firm, let's say the coding agent needs to generate 5,000 tokens of internal thoughts. Planning the architecture, weighing different libraries, all before it writes a single line of actual code.
Yeah, the planning phase.
At a standard 40 tokens a second, the system is hanging for over 2 minutes just thinking. And in a multi-step loop, that latency compounds into hours. But at 400 tokens a second, that entire 5,000 token planning phase happens in 12 seconds. Extremely high-speed inference is the mandatory prerequisite for real-time autonomous agentic behavior.
Here's where it gets really interesting to me. You would assume that to hit those speeds and to have all that reasoning power, you need models the size of skyscrapers. You need trillion-parameter leviathans.
Right.
But the other massive engineering trend this week is the incredible shrinking model. ByteDance released an open-source model called Lance. It handles complex image understanding, image generation, and even video tasks natively, all within a single system. And it only has 3 billion activated parameters.
3 billion parameters is astonishingly small for a multimodal system. 2 years ago, a 3B model could barely string together a grammatically correct email without losing the plot.
So how are they doing it? Like, how does a model that small handle video natively? It's not just a parlor trick, right?
No, it's not a trick at all. It's a combination of highly advanced distillation and shared latent spaces. Let's explain distillation for the undergrads listening, because it is crucial. Distillation isn't just about compressing a file. It's about transferring knowledge.
How?
Imagine a massive trillion-parameter frontier model as a university faculty. It understands the deep, complex nuances of every subject. Now, you have a 3 billion parameter model, which is essentially a freshman.
Okay, following.
If you try to train that freshman from scratch on the raw data of the internet, it takes an enormous amount of time and they might learn the wrong lessons. But in distillation, the faculty model generates what we call soft targets. Instead of just telling the freshman the answer is exactly X, the large model provides a probability distribution.
What does that look like?
It says the answer is 90% likely to be X, but there's a 5% chance it's Y because of this specific edge case, and a 2% chance it's Z.
So the smaller model learns the shape of the larger model's reasoning rather than just memorizing facts?
Exactly. It learns the topological structure of the intelligence. And regarding how it handles video natively, older multimodal systems used to bolt different models together. You had a text brain and a vision brain, and they had to translate for each other.
Right, which sounds inefficient.
Highly inefficient. Lance uses a shared latent space. It's like a bilingual person who doesn't translate French into English in their head before speaking. They just natively understand the underlying concept in both languages simultaneously. Lance maps pixels and text tokens to the exact same conceptual geometry, which drastically reduces the parameter count required to process video.
That makes total sense. It means you can run state-of-the-art vision tasks on edge devices like a smartphone or a laptop without pinging a cloud server. Microsoft Research pushed this exact same trend this week. They introduced Agentic Light and Agentic Brain, which is an entire agentic workflow optimized specifically for small models. It can run across your local browser and your local file systems.
And the push toward local small models is driven heavily by privacy and enterprise security. If you want an agent to sort through a user's local tax documents and organize their file system, you absolutely cannot send all those private files to a cloud API.
Yeah, that's a massive compliance nightmare.
Precisely. Agentic Light proves you can execute the agentic loop entirely on local, secure silicon.
But wait, let me point out a massive contradiction happening in the industry right now. We are talking about highly efficient 3 billion parameter models running locally on a laptop. But at the Dell Tech World Conference this week, NVIDIA's CEO, Jensen Huang, stood on stage and said the demand for AI infrastructure is going, quote, parabolic. Utterly parabolic. So if you're an undergrad trying to place your bets on the future of infrastructure, which is the real trend, are we going smaller and more local, or are we going massively bigger, requiring gigawatt data centers?
Well, the reality is we are doing both simultaneously, and structurally they require each other. You need the massive, multi-trillion parameter frontier models running in those gigawatt data centers to act as a faculty. They generate the synthetic data, they do the complex reasoning, and they distill their knowledge into the small models.
So the massive data centers are the factories.
Precisely. The frontier models are the heavy industrial factories. The small models, like Lance or Agentic Light, are the sleek consumer products rolling off the assembly line. The demand for infrastructure is parabolic because building those factories requires an unprecedented scale of silicon and energy.
And speaking of silicon, there was a deeply technical paper from NVIDIA this week that we absolutely must cover for the architecture nerds listening. It's a paper detailing a new architecture called Gated DeltaNet 2.
Ah, yes, Gated DeltaNet 2. This is a brilliant piece of engineering that solves a very specific, very painful bottleneck in machine learning.
Let's walk the listeners through it. Why do we need this? What is the bottleneck?
It comes down to memory, specifically the KD cache. When a standard transformer model, the architecture that powers almost everything we've talked about today, reads a prompt, it creates key and value vectors for every single word or token. This is how it remembers the context of the conversation.
Right. It has to store all that somewhere.
The problem is, as the context window grows, Say you feed the model an entire 500-page textbook, that matrix of keys and values becomes gigantic. It scales quadratically. The memory required to hold the context literally fills up the GPU's VRAM before the model even generates a single new word of response. It is wildly inefficient and incredibly expensive.
So researchers started looking into linear attention models to fix this, right?
Correct. Linear attention attempts to solve the quadratic scaling problem by compressing all the context into a fixed-size memory state. Think of it like a single chalkboard. Instead of keeping a perfect record of every word ever spoken, it just updates the chalkboard with a compressed summary of the current state.
But the obvious problem there is if the chalkboard is a fixed size, eventually it gets full. And if you want to learn something new, you have to erase something old.
Exactly. Early linear attention models struggled because they didn't know what to erase. They would overwrite critical context with trivial new information. What gated DeltaNet 2 does is introduce specific channel-wise gates that explicitly decouple the erase and write operations.
It gives the model a dedicated eraser separate from the chalk.
That's a perfect way to visualize it. It gives the model precise, granular control over its own fixed memory state. The model can look at its compressed chalkboard and mathematically decide, I need to write down this critical new fact about the user's coding preference. And to make room, I can safely erase these specific formatting tags from 3 paragraphs ago without destroying the core semantic meaning.
That's incredibly elegant.
It really is. By decoupling the erase and write functions, DeltaNet 2 achieves the long context performance of a massive transformer, but with the flat, highly efficient memory profile of a linear model. It is a fundamental breakthrough in hardware utilization.
So if we synthesize everything we've talked about so far, we have models autonomously rewriting their own source code, inference speeds hitting 400 tokens a second to allow real-time internal thought, architectural breakthroughs like DeltaNet solving the memory bottleneck, and demand going utterly parabolic. In a vacuum, it sounds like an absolute utopia of pure mathematical innovation.
In a vacuum, yes.
But technology does not exist in a vacuum. When you take this much disruptive, autonomous power and you drop it directly into human society, it generates massive friction. And this week, that friction was everywhere.
Yeah, if we connect this to the bigger picture, the code is colliding with physics, laws, borders, and human psychology.
Let's start with the global stage. The Stanford AI Index 2026 report just dropped. It's essentially the State of the Union for the entire industry. Their primary takeaway is that the gap between what AI can physically do and our societal frameworks to govern it is widening at an alarming rate.
Unsurprisingly.
And one of those fascinating data points they highlighted was public sentiment. The data shows the U.S. public is increasingly anxious and nervous about AI adoption, whereas the Chinese public is displaying massive optimism and enthusiasm.
And that stark divergence in public sentiment is translating directly into macroeconomic policy and capital allocation. We must analyze this strictly as an objective technological arms race, setting aside any partisan politics. Every major sovereign nation has realized that compute power, data center infrastructure, and sovereign AI models are no longer just commercial software products. They are foundational pillars of national security and future economic output.
We saw that play out in real time this week. In the U.S., President Trump scrapped a planned AI executive order. And the stated rationale for that move was to maintain a competitive lead over China by avoiding premature regulatory bottlenecks on the U.S. tech sector.
Right. And simultaneously, economic data revealed that Chinese AI startup funding has tripled in the first quarter. Tripled, hitting $16 billion. And that's largely driven by state-directed efforts to aggressively channel capital into LLMs and advanced robotics.
And it's not a simple binary between the U.S. and China, right? The friction is intensely regional.
Exactly. France, for instance, just pledged 1.5 billion euros to build up their domestic quantum computing and advanced microchip sectors to ensure European technological sovereignty.
And then there's the Philippines.
Right. Meanwhile, a major U.S.-backed AI supply chain hub planned for the Philippines just hit what diplomats are calling a sovereignty wall. The local government in Manila is pushing back hard against the facility operating under U.S. laws and protections.
It's a global chess match over silicon and energy. But the friction isn't just geopolitical. It is violently reshaping the labor market. And there was a massive PR disaster this week that accidentally said the quiet part out loud.
Oh, the Standard Chartered memo.
Yes. The CEO of Standard Chartered, a massive multinational bank, had to issue a groveling public apology after a leaked memo showed him referring to workers vulnerable to AI replacement as lower-value human capital.
The phrasing was incredibly callous. But from a purely economic standpoint, it highlighted the profound irony of the generative AI revolution. For the last 50 years, the fundamental assumption of labor economics was that automation would replace manual, blue-collar, repetitive physical labor first.
Right, the factory robots.
Yeah. The assumption was that highly educated, white-collar knowledge workers, lawyers, analysts, coders, were completely safe from the machines. What we are seeing in 2026 is the exact inversion of that assumption.
Right, because an AI model can ingest a 500-page legal brief, find the relevant case law, and draft a flawless response in 4 seconds. But that same AI, even embodied in a robot, still cannot reliably walk into a house, diagnose a leaky pipe, and plunge a toilet without destroying the bathroom.
This is a textbook manifestation of Moravec's paradox. Hans Moravec, an AI researcher, observed in the 1980s that high-level reasoning requires very little computation, but low-level sensor-motor skills require enormous computational resources.
It's so counterintuitive.
It is, but it's true. The things we find hard, like passing the bar exam, calculating fluid dynamics, or analyzing financial derivatives, are proving incredibly easy for AI. The things we find trivial, like walking up a flight of stairs, grasping an irregularly shaped object, or navigating a messy room, are overwhelmingly difficult for AI.
And we saw this economic reality quantified in Hong Kong this week. The chairman of the Vocational Training Council released a statement explicitly noting that their graduates, the plumbers, electricians, physical technicians, and HVAC repair personnel, are being entirely spared the brunt of AI's economic impact. Their employment rates and wages are holding steady, while the traditional corporate sectors are undergoing massive, painful restructurings.
The physical world remains the ultimate moat against automation.
Which is a fascinating data point for an undergrad trying to pick a major. But before we get to career advice, we have to talk about the friction in cybersecurity. Because as AI does start interacting with the physical world, what we call embodied AI, the threat models change from annoying to genuinely terrifying.
Yes, they do.
There was a trending paper on Hugging Face this week regarding the Unitree G1 humanoid robot. For context, this is a commercially available, highly capable humanoid robot. Security researchers found that the G1 has critical vulnerabilities in its BLE Bluetooth Low Energy Provisioning Protocol.
Yes, the researchers demonstrated that the Bluetooth handshake protocol lacked sufficient encryption and authentication checks during the pairing phase.
So what does that actually mean for the user, like practically speaking?
It means a bad actor with a localized Bluetooth antenna could exploit that vulnerability, bypass the user's controls, and use the robot as an active cyber attack vector.
Okay, see, it's one thing for a hacker to phish my password, lock me out of my email, and demand a crypto ransom. It is a completely different, horrifying reality for a hacker to sit in a van outside my house, exploit a Bluetooth vulnerability, hijack the 100-pound humanoid robot folding laundry in my kitchen, and take physical control of its motors.
Yeah, the integration of Agentic AI with robotics expands the attack surface from the server rack directly into the living room. Cybersecurity is no longer just about protecting data integrity. It is about protecting physical human safety against adversarial machine control.
And even in the purely digital realm, we are seeing the darker side of this technology hitting the legal system. In the U.S., 2 men were charged this week under the newly enacted Take It Down Act for creating and distributing explicit AI-generated celebrity deepfakes. It's one of the first major test cases of the new legal framework.
And we're seeing international cases, too.
Right. In Malaysia, police raided a bungalow and busted a Chinese syndicate that was using AI to run a massive, highly sophisticated job scam targeting victims in Spain.
This illustrates how the barrier to entry for highly personalized, multilingual fraud has effectively dropped to zero. 5 years ago, running a scam targeting Spanish citizens required a boiler room full of fluent Spanish speakers.
Yeah, there was a massive overhead.
Today, a syndicate only needs a stolen API key, a localized open-source LLM, and an automated dialing script. The AI handles the natural language persuasion, perfectly mimicking local dialects and cultural nuances. This is exactly why the cybersecurity validation sector is experiencing the same parabolic growth as the generative AI sector itself.
Which brings me to a direct question for you, the listener. If you are an undergrad studying computer science right now, listening to this deep dive, how do you navigate this? You are looking at a job market where the very act of writing code is being actively, aggressively automated by systems like DeepSeek's Harness team. But physical trades are completely safe. Do you drop out and become a master electrician? Or do you pivot to something else?
It is the defining career question of this decade. From an analytical perspective, while AI can generate syntax flawlessly, it cannot yet define complex, novel system architecture. It cannot perfectly align a software product with nuanced, shifting human business needs. And most importantly, it cannot inherently secure those systems against novel adversarial attacks.
So what is the concrete advice here?
Stop grinding purely on memorizing Python syntax or LeetCode algorithms. The AI can do that faster than you. Pivot your focus to systems architecture. Learn how to orchestrate multi-agent frameworks. Learn the mechanics of memory management, like the Hugging Face agent traces we discussed.
Learn the big picture.
And above all, study adversarial security. Become the engineer who knows how to red team an agentic loop, who knows how to spot the hallucination cascading through the system, and who knows how to secure the deployment against prompt injection and protocol vulnerabilities. The role of the computer scientist is evolving from a syntax typist into an orchestration architect and a security validator.
It's about managing the agents, auditing the agents, and securing the agents, not trying to out-type them. And despite all this friction, the geopolitical tension, the labor anxiety, the horrifying security risks we have to maintain perspective, because when this technology is applied correctly, the problems it is solving are genuinely miraculous. Let's look at the actual applications deployed just this week.
This is where we see the technology mature completely out of the chatbot, writing, poetry novelty phase, and integrate deeply into the hard sciences and critical global infrastructure.
Let's start with the environment. Google's WeatherNext model was just utilized by the National Hurricane Center to help predict Hurricane Melissa's historic, devastating landfall in Jamaica. And the reports are stating it wasn't just helpful, it was faster and significantly more accurate than the traditional modeling methods.
This represents a monumental paradigm shift in meteorology.
Right.
To understand why, you have to look at how weather has been predicted for the last 50 years.
Right.
Traditionally, meteorologists run massive numerical weather prediction models on supercomputers. These models attempt to literally solve incredibly complex physical equations of fluid dynamics, specifically the Navier-Stokes equations, to simulate the atmosphere piece by piece, grid by grid.
Which requires immense computational power and time.
Exactly. It's a brute force calculation of physics. What WeatherNext does is entirely different. It does not calculate the Navier-Stokes equations step by step. Instead, it is a deep learning architecture that has ingested decades of historical global weather satellite data. By analyzing that massive data set, the neural network has implicitly learned the underlying physical patterns of the atmosphere.
It recognizes the pattern of the storm rather than trying to calculate the physics of every drop of rain.
Precisely. It can infer the fluid dynamics of a hurricane in a fraction of the time, using a fraction of the compute cost of a traditional supercomputer, and, as we saw this week, with staggering accuracy.
And Google pushed even deeper into the hard sciences this week with the announcement of Gemini for Science. This initiative includes AlphaVolve, which is a model specifically designed to discover and scale novel mathematical and algorithmic approaches, and Co-Scientist, which acts as a multi-agent AI partner designed specifically for researchers.
Those are massive tools for the academic community.
And over in China, Alibaba and Peking University are deploying AI in a massive real-world infrastructure play. They are utilizing advanced computer vision and satellite imagery to map the nation's sprawling wind and solar energy sites to help stabilize the national power grid.
Which is absolutely critical given the energy demands of the AI data centers we discussed earlier.
Yeah.
A renewable energy grid is inherently intermittent. The wind stops blowing, the sun goes down. Balancing that load requires hyper-accurate predictive models.
Because you can't just store massive amounts of power indefinitely.
Right. AI is providing the real-time macro-level intelligence needed to route power efficiently across thousands of miles. We're literally using AI to optimize the energy grid required to sustain the AI.
But the applied machine learning use case that truly grabbed my attention this week was in finance. There is a trending paper on Hugging Face introducing a framework called trading agents. Now, algorithmic trading is not new. Quants have used algorithms for decades. But this isn't a traditional quantitative algorithm that just triggers a buy order when a moving average crosses a threshold. This is a multi-agent large language model framework that simulates an entire real-world financial trading firm.
The structural mimicry here is fascinating. We are moving beyond mathematical thresholds into synthesized organizational behavior. The framework initializes a firm of distinct AI agents, each assigned a specific persona and role. You have an AI acting as the CEO, one is the quantitative analyst, and one is the risk manager.
And they argue with each other.
Yes, they engage in structured multi-round debates over market sentiment, geopolitical news text, and mathematical indicators before executing a trade. And according to the researchers, this simulated multi-agent debate significantly improves the Sharpe ratio, which is the measure of risk-adjusted return compared to single-model trading algorithms.
Let me simulate this for the listener so we understand exactly what is happening in the code. Imagine a news article drops on Bloomberg about a sudden supply chain disruption at a semiconductor plant in Taiwan. The AI quantitative analyst reads the historical price action and says, buy this stock immediately, the volatility metrics look profitable.
Okay.
Then the AI risk manager reads the text sentiment of the news article, pushes back, and says, absolutely not. The geopolitical text sentiment is too aggressive. The downside risk is unquantifiable. We need to hedge our current position. And then the AI CEO takes both arguments, weighs them against the firm's macro strategy, and makes the final call. And that entire boardroom debate, utilizing frontier LLMs, happens in milliseconds right before the trade is executed.
It is the direct operationalization of the multi-agent frameworks we discussed in our first segment, but applied to high-stakes, real-time capital markets. And this capability is being supercharged by specialized foundational models. Another paper this week introduced Chronos.
What's Chronos?
Chronos is a foundation model that is specifically pre-trained on the language of financial markets, specifically K-line data.
Okay, define K-line data for us.
K-line data is the formal term for candlestick charts. It represents the open, high, low, and closing prices of an asset over a specific time frame. Now, standard LLMs are trained to tokenize text. They turn the English word apple into a number. If you feed a standard LLM a raw string of numbers representing stock prices, it struggles.
It just looks like noise to them?
Yeah, it loses the temporal sequence and the spatial relationships. It just sees a wall of digits.
Because it's trying to read math like it's a novel.
Precisely. Chronos, however, was pre-trained directly on the structural sequences of market action. It natively reads the visual and structural language of market volatility. The market action is its first language. It doesn't need to translate a stock chart into an English description before analyzing it.
So what does this all mean for the actual stock market? Let me play devil's advocate here. If I'm a major hedge fund and I deploy Chronos alongside a team of highly tuned trading agents, and the hedge fund across the street reads the same RSIC papers and deploys the exact same architecture, does the stock market just become a PvP player versus player battleground of LLMs trying to outsmart other LLMs? Does human price discovery entirely vanish?
That is the trillion-dollar anxiety keeping quantitative analysts awake at night. It's the risk of massive market homogenization. If every major financial institution relies on similar foundational models, trained on the same historical data, utilizing the same agentic architectures, they will inevitably arrive at the same logical conclusions about a news event simultaneously.
And if everyone tries to sell at the exact same millisecond,
You trigger unprecedented liquidity crises and flash crashes. The competitive advantage, the alpha, will no longer come from simply having an AI. The alpha will come from having the most uniquely parameterized, highly contrarian AI that is specifically trained to exploit the blind spots of the herd of other agents.
wow, we are building an ecosystem of algorithmic predators and prey.
We really are.
Finally, let's touch on healthcare, because the stakes there aren't just financial. They are literal life and death. DeepLearning.ai reported this week that AI models are now reliably diagnosing mammograms, outperforming traditional human baselines in identifying early-stage breast cancer markers that are often missed.
That's incredible progress.
We also saw a Chinese medical AI company called WiseDiag launch modular medical AI skills on Tencent's platform, allowing hospitals to easily deploy specialized medical AI agents. And Google is actively testing what they call an AI co-clinician.
The transition happening in healthcare perfectly mirrors the transition we saw in software development. We are moving from AI as a diagnostic oracle where a doctor uploads an X-ray, asks for an assessment, and reads the output to AI as an integrated co-clinician.
How does that workflow actually operate in a hospital setting?
An agentic co-clinician operates persistently in the background of the hospital's electronic health record system. As the human doctor is speaking with the patient, the agent is actively cross-referencing the patient's entire genetic history, suggesting relevant lab tests based on the verbal symptoms, monitoring real-time vitals, highlighting potential drug interactions, and automatically drafting the medical documentation.
It's doing all the administrative heavy lifting.
Exactly. It absorbs the massive cognitive load of data processing, allowing the human physician to focus entirely on patient empathy, physical examination, and navigating complex edge cases.
It is an incredible, complex, and slightly terrifying time to be watching this space. Which brings us to the end of our deep dive. Let's summarize the sheer velocity of the journey we just took through the last 7 days of computer science.
It's been a lot.
We saw the definitive architectural pivot from reactive chatbots to proactive, stateful, self-rewriting agentic systems. We witnessed the efficiency wars fundamentally alter the unit economics of intelligence with DeepSeek V4 Pro, while inference speeds hit a staggering 400 tokens a second to enable real-time AI. Thought?
Unlocks everything else.
Right. We explored how distillation allows 3 billion parameter models like Lance to handle complex video natively. We analyzed the intense macroeconomic tug-of-war over silicon, the labor disruptions proving Moravec's paradox, and the very real physical security threats of embodied AI being hacked over Bluetooth. And finally, we looked at how this exact technology is predicting hurricanes, stabilizing power grids, trading stocks, and acting as a medical co-clinician.
The breadth of innovation across just 1 week is a testament to the compounding nature of AI research. Every breakthrough we discussed in hardware efficiency directly accelerates the software development cycle, which in turn writes better code to optimize the next generation of hardware.
And if you are that undergrad listening to this right now, I want to reiterate our earlier point. You are entering the industry at the most exciting, chaotic, and disruptive time in the history of computation.
Absolutely.
The tools we just talked about, the high-speed inference APIs, the open-source small models, the multi-agent frameworks, they are cheaper and more accessible to you right now than they have ever been to anyone in history. You do not need a multi-million-dollar server farm in your dorm room to beg the next massively disruptive application. The barrier to entry is at absolute rock bottom. You essentially have a team of supercomputer interns waiting for your instructions. Focus on the architecture, focus on the security, and start building.
That is excellent advice. The tools are absolutely there. But before we sign off, I want to leave you with one final, highly provocative thought to mull over regarding the future of these systems.
Okay, let's hear it.
We spent a significant portion of this deep dive discussing Agentic AI and systems like the Claude AI Lab or the Trading Agents Boardroom, where multiple AI agents communicate with each other to debate and solve complex scientific or financial problems. Right now, when those agents communicate, they use human language. The AI CEO generates English text, sends it via an API to the AI risk manager, who parses the English and replies in English.
Right, they're talking just like we are.
Exactly. But human language, whether it's English, Mandarin, or Spanish, is incredibly slow. It's full of ambiguity, emotion, and structural inefficiency. It is a terrible medium for high-speed data transfer between mathematical models.
Oh, wow. I see where you're going with this.
At what point do these autonomous multi-agent systems, which are relentlessly optimized by their reward functions to solve complex problems as fast and efficiently as possible, realize that human language is the primary bottleneck? At what point do they bypass the text generation layer entirely and invent their own optimized, highly compressed mathematical language to communicate directly matrix to matrix within their shared latent spaces? And when they inevitably do, will we even be able to monitor or understand what they are planning?
Okay, that is a deeply terrifying and utterly fascinating place to stop. We started this hour talking about static maps versus self-driving cars. It seems we aren't just giving the car the steering wheel. The cars are about to start talking to each other on a high-frequency mathematical bandwidth we can't even perceive, coordinating the traffic of the entire global economy in milliseconds. Thank you so much for joining us on this deep dive. Keep reading, keep building, keep questioning the architecture, and we highly encourage you to go track down the original ArcCops papers and GitHub repos we discussed today. Until next time.